What is the definition of a simple harmonic oscillator? What are the two examples we studied considering simple harmonic oscillators? Well, if we start with the first question, a special type of periodic motion where the restoring force is directly proportional to the displacement and acts in the direction opposite of that displacement. What does that mean? It means that you have a restoring force that's pointing towards the equilibrium. The closer you are to the equilibrium, the smaller the force. As you move further and further away from that equilibrium, the restoring force is going to get larger. So the restoring force is proportional to the displacement. As one gets bigger, so does the other. And it's in the opposite direction, meaning if you move in the positive direction, the restoring force is in the negative direction, and vice versa. What are the two examples we've studied? Think about all the problems we've been working on. We've been working on pendulums and springs. The springs can be either vertical or horizontal. Number 2, what factors affect the period of a simple pendulum? What factors affect the period of a mass on a spring? In order to calculate these or answer the problem, we need to know what the formula is, and from the formula we'll know what variables are important. The period of a pendulum can be calculated as 2 pi times the square root of L over G. L is the length of the pendulum. G is the acceleration of gravity for wherever you're located. If on Earth and not otherwise stated, we will use 10. The period of a spring can be calculated as 2 pi times the square root of m over k. M is the mass attached to the spring, and k is the spring constant. Number 3, why are some oscillators, such as a marble rolling in a U-shaped tube, not examples of simple harmonic motion? If we look at a U-shaped tube, the bottom portion is a semicircle, and it would work for our purposes of simple harmonic motion. But if you look above my dotted line, if I've got an object that's moving, and that's my marble inside my U-shape area, if it's moving in that vertical area, as it goes further up, it is moving away from equilibrium, but the restoring force isn't changing. It's moving vertical to gravity, and gravity's not changing. So the reason why it doesn't work is that the restoring force is not proportionate to displacement in this case. The restoring force, gravity, is not increasing as you roll straight upwards. It's only in that semicircle area where you're getting a different component of gravity. But once you get fully vertical, if you go any further, the restoring force won't be directly proportional to the displacement. Number 4, a simple pendulum is constructed by hanging a 3 kilogram mass on the end of an 0.8 meter long string. So I'll get that kind of drawn. The pendulum is pulled back to a height of 0.2 meters and released. So we'll pull it to the right then, we'll say, and it'll be 0.2 meters higher than it was before. The length is still 0.8. The length of the pendulum hasn't changed. Calculate the period of such a pendulum. Well, the period of a pendulum is 2 pi times the square root of L over G. So in our calculator, we'll use 2 times pi times the square root of 0.8 divided by 10. since this pendulum is most probably near or on Earth. When we calculate the period is in seconds. Don't forget, period is how long does it take to do the full cycle one time? And we get 1.78 seconds for the period. At what time will the mass reach its maximum velocity? Well, it's at amplitude right now, on the right side. In order to complete a full period, it must move all the way to the left and then all the way back to the right where it started, completing a full cycle. Equilibrium is reached at 1/4 the period and at 3/4 period. So if we do 1/4 the period that we calculated, 1/4 of 1.78, we'll find out when it first reaches equilibrium. 1.78 divided by 4 is 0.45 seconds. How would your answer to each of the above change if the mass of the pendulum bob were doubled? There's no change. We don't factor in the mass of the pendulum bob in the calculations for a period. Number 5, a 3 kilogram mass is attached to the end of an ideal spring constant 100 newtons over meters, which is hanging vertically. The mass is pulled down 0.2 meters and released. So the 0.2 meters would be our amplitude. That's how far it's displaced from equilibrium, and it will go 0.2 down and 0.2 above equilibrium as it oscillates. Calculate the period of the mass. The period, because it's on a spring, would be calculated as 2 pi times the square root of m over k, mass over spring constant. So we're calculating the period. We've got 2 pi times the square root of 3 divided by 100. And we calculate that. It looks like we get 1.09 seconds. At what time will the mass first reach its maximum velocity? Again, it's at amplitude. It will reach equilibrium, highest velocity, at 1/4 a period. It's at the bottom amplitude, 1/4 a period to equilibrium, 1/4 a period to top amplitude, 1/4 back to equilibrium, 1/4 back to the bottom amplitude. So we're just going to take that 1.04 divided by 4, and we get 0.27 seconds. How would your answer to each of the above change if the mass were doubled? Well, they're both going to increase because mass is a factor in our calculations for the period of a spring. It would definitely increase. Increasing mass would increase the period. Since we're doubling it, the period would increase by a factor of square root of 2. We know this because if we just make everything a 1 and then we plug in our changes, so we have 1 times the square root of 1 over 1. And if nothing changes, then it equals 1 times the change, nothing changes. But here we're going to take out that 1 where the mass goes, and we're going to put in a 2. And then we're going to simplify so we can see what the change is for the period. It'd be the square root of 2, which equals 1.41, I believe. So our period is going to be 1.41 times as long as it was. So it's getting longer, more time. What would the spring constant have to be to allow the 3 kilogram mass to oscillate 4 times per second? 4 times per second is a frequency. Because frequency tells us how many times can the oscillation occur every second. We'll need the inverse of the frequency, the period, to calculate this problem. So if you can do it 4 times in a second, how long does it take to do it once? Well, it'd be the inverse of 4, which would be 1 over 4, or 1/4, 0.25. So 0.25 is our period, and 0.25 is equal to 2 pi times the square root of m over k. They've told us the mass is 3, and we're solving for a new k. So now that we have 0.25, what we can do is divide by 2 and then divide by pi. If you want to divide by 2 pi together, make sure you put it in parentheses, 0.25 divided by open parentheses 2 pi close parentheses. Once we've divided that over, we get about 0.04 is equal to the square root of 3 over k. So I want to square both sides now. If I square both sides, I'll get a number is equal to 3 over k, and then I can just take my 3 and divide by that number to get my spring constant. Here I get 1894.96. Depending on how you round or where you round, you'll get something close to that. Number 6. A block of mass 5 kilograms is initially at rest next to an ideal spring constant 1,000 Newton seconds, as shown in the diagram. A second block of 2 kilograms approaches the first block at 35 meters per second, colliding with and sticking to it at time equals 0 seconds. So that's when the experiment begins. After a collision, the blocks move together in simple harmonic motion. So what we have is the 5 kilogram block is at equilibrium with the spring, and when they hit, that's when it'll start in motion. So this system is going to start its motion at equilibrium, moving to the right, moving towards amplitude where we compress the spring. At what time after the collision will the 2 blocks first come to a rest? Well, if we're only moving from equilibrium to amplitude, that's 1/4 of a period. So if we calculate the period, we can then determine, well, 1/4 of the period is from equilibrium to amplitude. The period is 2 pi times the square root of m over k, 2 pi times the square root of 7 over 1,000, which is 0.53 seconds. If we divide that by 4, we get that 1/4 of a period motion from equilibrium to amplitude, and that gives us 0.13 seconds. B says, what is the maximum compression of the spring? So we're looking for x displacement at amplitude. We want to know how far is it going to be compressed. And for this question, when I'm looking at this, what I'm thinking is well, at equilibrium, I've got max kinetic energy. At amplitude, all of my energy is my my spring potential energy. So I can set my kinetic energy at equilibrium equal to my spring potential at amplitude. And if I do that, I can then solve for x at that point. The problem is my formula, I don't know what the velocity is at the after the collision when it's one big mass. So let's use our conservation of momentum. We can say that the 2 kilogram mass is moving at 35 meters per second plus the 5 moving at 0 is equal to the combined mass of 7 times their velocity. When we do that, we find that the combined mass velocity is 10. We can now put that into our formula. At equilibrium, we have 1/2 times the mass of 7 times 10 squared, the velocity we found after the collision, is equal to 1/2 times k, they gave this to us, 1,000, times x squared. We're going to solve for x. Yes, the 1/2s cancel on each side. 7 times 10 squared is 700, is equal to 1,000 times x squared. Divide by 1,000, and then square root. So we'd get the square root of 0.7 would be the displacement at amplitude at maximum compression. .84 is what we get. Now that we have amplitude, we know the total displacement, the total possible displacement, we can do C and D a little bit easier. What is the position relative to the equilibrium position of the 2 blocks 1 second after the collision? Well, if we're determining position based on time, ideal formula would be position is equal to amplitude times the cosine of 2 pi times the frequency times that time point. It's a mouthful, but it works. Make sure you're in radian mode. So the position that we're looking for is equal to the amplitude 0.84 times cosine of 2 times pi times the frequency. But what I'm going to do for frequency is I'm just going to use the period and then the x to -1 button that's located right above my x squared on my calculator. So I'm just going to type in 0.84 cosine, that opens the parentheses for me, 2 pi times 0.53 x to the -1 times 1 close parentheses. And again, that x to -1 is just a single button right above the x square on my calculator. When I hit enter, that will give me my, my position, 0.64 meters. What is the maximum acceleration of the two blocks? Well, we know the force of the spring is kx. It's really negative kx, but kx. And we know force is mass times acceleration. So if force is mass times acceleration and it's kx, we can say ma is kx, divide the m over. Acceleration is spring constant times displacement divided by mass. Just combining two formulas that both equal force. In this case, k is 1,000. Maximum acceleration happens at the amplitude, maximum displacement 0.84, and divided by the mass of 7. So we're going to take 1,000 times 0.84, which should be like 840, and divide that by 7. We get 120 meters per second square for our acceleration. All right, we've got a graph below that shows us the position of a particle when it is in simple harmonic motion. Since this is a position graph, we know that the slopes give us velocity. We know that anything above the horizontal axis is in a positive position relative to the origin, and anything below the horizontal axis will be in a negative position. What is the period of motion of this particle? It's going to be 10 seconds because we're going to find two places on our graph. Both times we're crossing the equilibrium, and both times we have a positive slope. We can also go from peak to peak or trough to trough. When I said peak to peak, that would be crest to crest. At what time will the particle first come to rest? So we need to find the first time that we have a slope of 0. We find that at about 2.5 seconds. There's another one at 7.5, then 12.5. Anytime that slope has a 0 slope, that's a 0 velocity. At what time will the particle first reach its maximum negative velocity? Maximum velocity happens at equilibrium. Maximum negative velocity would happen when the slope is negative at the equilibrium. We see that happens at 5 seconds. So at time equals 5 seconds, maximum negative velocity. At what time will the particle first reach its maximum positive acceleration? Acceleration occurs when you're away from the equilibrium. You have acceleration. The further you go, the greater you're going to have it. And we know that acceleration points towards the equilibrium. So positive acceleration would be when displacement is negative, and maximum acceleration would occur when you have the maximum negative position. So time 7.5 seconds. At what time does the particle first have its maximum kinetic energy? Maximum kinetic energy will happen at maximum velocity. Kinetic energy doesn't care about the direction of the velocity because the velocity is being squared. So we get maximum velocity at equilibrium, and we actually started at time equals 0 at maximum velocity. So maximum kinetic energy is maximum velocity, which is located at the equilibrium, like I said. Assume that the particle has a mass of 2 kilograms, which is oscillating on the end of an ideal spring. Calculate the spring constant of the spring. Well, we know the period is 2 pi times the square root of m over k. Looking at the graph, we're able to determine how long the period is, and we said 10 seconds is equal to 2 pi times the square root of, they gave us a mass of 2, and we're going to divide that by k. So again, 10 divided by 2 is 5, and then divide by pi. If you want to divide by 2 pi, make sure you put that in parentheses. Otherwise, the calculator will think that you're dividing by 2 and then multiplying by pi. Either way, we get 1.59 is equal to the square root of 2 divided by k. Square both sides, and then you're going to take the 2 and divide by what you got with 1.59 squared. And that will get us our K. 0.79 is our spring constant. What's the magnitude of the maximum acceleration of the mass? Well, again, acceleration is net force divided by mass. In this case, the net force is the force of the spring, which is calculated as kx. So acceleration is force divided by mass. Force is kx, so kx divided by the mass. K we said was 0.79. And x is 3 from the graph previous. That's our maximum amplitude. And divide by 2 the mass they give us above. So 0.79 times 3 divided by 2 will equal 1.185 meters per second square, or of course you can round that down to 1.19. On the graph below, plot the velocity of the particle. We know that our particle is starting in a positive. It then decreases down to a velocity of 0, coming to a stop at 2.5 seconds, and then increases in a negative direction with maximum negative velocity at 5 seconds, slowing back down to 0 at 7.5. Has a positive velocity with maximum at 10 seconds, slowing back down to a stop at 12.5, and then it just kind of repeats. Once we see what the pattern is, we can kind of take that pattern and draw. And that's the graph we get.